Hello students, now we are going to discuss about the cyclic structures of glucose molecule. Let's start with our very best friend glucose. The structure was something like this. Now in this case, what we can suggest is that the fifth carbon or the lowest chiral center has OH onto the right hand side. That means this entire molecule is not only glucose but it would be called as D-glucose. Similarly, we can also say that now this entire molecule is represented as Fischer projection formula. So what if we want to make a Haworth's projection formula out of this? Let's see how this can be done. So what our aim is to prepare an Haworth's projection formula. For this, what we need to do, first of all, we need to mark the carbon atoms. So let's do this. We have total of 6 carbon atoms. We will just mark them right now. Out of this, the first priority would go with the aldehydic group. So first we would mark the aldehydic group. Next comes the number of the last carbon. That is nothing but a primary alcoholic carbon. So we would mark that one as well. Now, what we would do next is we would number all the carbon atoms. So do we have 6 carbon atoms right now? Yes, we have 6 carbon atoms. Next, we would draw lines onto the second, third, fourth and fifth carbon atoms. Now, as we have drawn these lines, it suggests that there are some groups which lie above the plane, whereas there are some groups which lie below the plane. Let's see this. Now, what we need to remember is all groups which come onto the right hand side, that means groups into your green box right now, would be nothing but below the plane. So we would just write them. And all the groups which are on the left hand side would be the groups coming on above the plane. So we will also write them. And now we have learnt into the previous module that to prepare a pyranose ring, we need the attacking OH onto the fifth carbon atom. So now what we would do is we would just invert or flip the positions. Let's see how. H goes to the position of OH, OH to the position of CH2OH, CH2OH to the position of H. So what we get right now is nothing but a structure like this. In this structure, aldehydic group remains as it is. But now, instead of CH2OH, you have OH and next H and CH2OH onto their respective positions. Remaining all the groups, they are once again same. So you just fill them up and finally we would get a structure something like this. Now in this structure, a very important thing happens. We all know the carbon double bond oxygen is a polar bond where carbon is partially positive, oxygen is partially negative. So what happens? In this case, OH represents O with 2 lone pairs. This oxygen donates 1 lone pair towards the carbon and the oxygen donates 1 lone pair towards carbon. So what would happen now? You would get a compound in which hydrogen would go and attack onto the double bond O, giving you OH. Let's see how is this possible. But before going on with the attack, we need to remember an important point learnt in haloalkanes, haloarenes, that if you have a carbon atom which is planar, attacks can be from 2 sides and thus it will result into 2 different compounds. Let's see those 2 different compounds. First would be this, second would be this. Now, in the first compound and in the second compound, what is the difference we need to know? Then, the very first difference, or rather the very first similarity which we can calculate as of now is both these structures are similar to pyran. And if they are similar to pyran, they are pyranose. As they are obtained from D-glucose, there are D-glucopyranose. And now what we can say is, onto the first carbon atom, that is onto the aldehydic carbon or the anomeric carbon. OH is present on below the group. Therefore, this compound would be called as alpha, whereas if onto the first carbon or the anomeric carbon OH is present above the group, it would be called as beta form. So we have two forms, alpha D-glucose and beta D-glucose. Out of this, now we need to remember a very important point in this case is the first carbon atoms in both the cases are anomeric carbons. What do we mean by anomeric carbons? Then these are the only carbon atoms which are being flipped. Otherwise, the entire compound is same. And minded students, these carbon atoms are optically active as well. So we have only these carbon atoms which are flipped. Therefore, we can say that as alpha D-glucose and beta D-glucose both consist of anomeric carbons, both are anomers of each other. So what we can conclude in this entire discussion is that cyclic structure results into alpha form and beta form, which are anomers of each other, given a name as alpha D-glucopyranose and beta D-glucopyranose. This was all about the cyclic structures of glucose. Meet you in the next module. Till then, thank you, students.